Right now, as you sit in the quiet of your room, the planet you're standing on is rushing toward a point in the dark that you cannot see. You feel perfectly still. Your coffee sits undisturbed in its cup. The air around you is calm, and the world outside seems locked in a familiar, comfortable rhythm. But beneath that stillness, the physics of our solar system are in relentless, silent motion. Earth is currently travelling at roughly 30 kilometers per second in its orbit around the Sun. In the time it took you to hear that sentence, you and everything you have ever known moved roughly 150 miles through the void. We're closing a gap of approximately 140 million miles that separates us from the red desert of Mars. This distance is a confirmed measurement, a real physical expanse, but to the people who will one day cross it, this gap is better understood not as miles, but as a wall of time, a silent signal delay that dictates the absolute limits of human survival. When the first crew finally crosses that threshold, they will not just be entering a new world, they will be stepping outside the protective sensory reach of everything that makes us human. If you find these kinds of deep investigations into the quiet, often overlooked realities of our universe interesting, subscribe now. The investigation begins with a signal, or more accurately the absence of one. To understand the isolation of Mars, we have to look back at the missions we think we understand, the Apollo landings. For decades, we have used the Moon as our mental template for space exploration. We imagine a crew leaving Earth, landing on a distant surface, and returning to a cheering crowd a week later. But the Moon is close, cosmically speaking. It is approximately 239,000 miles away. That is a distance so small that a radio signal travelling at the speed of light can cover it in about 1.25 seconds. When Neil Armstrong reported that the Eagle had landed, mission controllers in Houston heard his voice almost instantly. Houston was always there, a heartbeat away, providing what psychologists call a cognitive surplus for the crew. This real-time loop meant that the astronauts were never truly alone. They were merely the hands and eyes of a massive earthbound brain that shared their present moment. Mars offers no such luxury. At its closest approach to Earth, Mars is still 34 million miles away, 142 times farther than the Moon. At that distance, a radio signal takes just over 3 minutes to cross the gap. At its farthest point, when the two planets sit on opposite sides of the Sun, that distance swells to 250 million miles, and the delay increases to 22 minutes. This is not a technical limitation that we can engineer our way around. This is established physics. The speed of light is the absolute cosmic speed limit, and it means that a simple exchange, a question and an answer, will take at least 44 minutes. Think about a standard phone call. There is a moment, perhaps when you're calling someone halfway across the globe, when a half-second lag on the satellite connection makes the rhythm break. You talk over each other. You pause awkwardly. The natural flow of human exchange is severed by just 500 milliseconds. Now, multiply that delay by 2,640. On Mars, communication is not a conversation. It is correspondence. It is closer to writing a letter and waiting for the mail to arrive than it is to any form of human communication our species has evolved to understand. This temporal wall changes the fundamental nature of survival. Consider the historical moment on April 13, 1970, when an oxygen tank exploded aboard Apollo 13. The crew reported the problem, and less than 2 seconds later, Mission Control was working the problem. Telemetry data streamed into Houston in real time, allowing hundreds of engineers to see what the astronauts were seeing as it happened. This real-time loop saved 3 lives because help was already listening. Now replay that same scenario on the surface of Mars. An explosion occurs. A pressure seal in the habitat fails and the atmospheric alarm triggers. The commander keys the microphone and reports the emergency. That signal leaves the spacecraft and begins its long journey through the void. For the next 14 minutes, the crew is entirely, terrifyingly alone with the crisis. They must diagnose the problem, assess their options, and begin a fix before their distress call even reaches the ears of an engineer on Earth. By the time Houston receives the message and formulates a response, 28 minutes have passed since the alarm first sounded. In a situation where seconds matter, the crew is either already alive because they solved it themselves, or they are dead because they could not. Earth can only listen to the sound of a past that has already ended. This is confirmed by NASA's own research into communication delays, which acknowledges that Earth is removed from the decision-making chain during a Mars mission. This isolation extends beyond emergencies into the very texture of daily life. On Earth, we live inside a shared present. When something happens, news of it spreads across the globe in seconds, creating a common temporal experience for our entire species. A Mars crew is excluded from this. Their present is offset from Earth's by those light minutes. They cannot watch a live broadcast. They cannot join a video call with their families. They cannot share a meal over a screen in real time. They exist in a parallel timeline, informed about Earth's activities but unable to participate in them. This is a condition of sensory disconnection that has no precedent in human history. Every explorer before them, from Magellan to the researchers in Antarctica, maintained some form of real-time or near real-time connection to the human world. Even a sailor in the middle of the Pacific can radio for help and expect a response in seconds. The Mars crew will be the first human beings to live beyond the sensory reach of their own world. From the Martian surface, Earth is not a blue marble. It is a bright point of light in the pre-dawn or post-sunset sky, indistinguishable from a star except by its position and brightness. It is a coordinate, an abstraction, a smudge of light that you can cover completely with the tip of your smallest finger held at arm's length. Everything you have ever loved, every person you have ever known, and the entire human civilization that built the rocket you arrived in fits behind your smallest fingernail. As the weeks turn into months, the bonds that connect the crew to Earth do not snap. They stretch. They become thin and translucent. People on Earth continue their routines. Seasons change, holidays come and go, and restaurants the crew once loved close and are replaced. The crew watches their own lives continue without them, transmitted in delayed fragments across millions of miles of empty space. They become observers of Earth rather than participants in it. This gradual disconnection is what turns a round-trip mission into a psychologically one-way journey. The crew must invest emotionally in where they are, the habitat, the landscape, and each other, simply to survive. Every unit of emotional energy directed toward Mars life is a unit withdrawn from Earth life. By the time the launch window for return arrives, roughly 500 days into the surface stay, the version of Earth they carry in their hearts may no longer exist. They will have crossed an invisible line where leaving becomes its own kind of arrival, and arrival becomes its own kind of loss. This is the first and most profound reason why the first people on Mars may never return. It is not just about the physics of the journey. It is about the quiet, accumulating rewriting of what it means to be human in a place where home is just a star. But even if the mind adapts to the silence, there is another, more physical tax that the universe demands for crossing this gap, a tax paid in the very architecture of the human body. This is established science, and the data shows that the moment you leave Earth's gravity, your body begins to become something else entirely. That physical transformation begins with the very thing that holds you up right now, your skeleton. The energy required to even attempt to bring that changing body back to Earth is a debt we may not yet be able to pay. Right now, as you sit in the stillness of your room, you're being held in place by an invisible debt. You feel nothing, no movement and no strain, but you're currently pinned to the floor by the most familiar and relentless force in the universe, gravity. Every single day of your life from the moment you were born, this force has been pulling you downward, tethering you to the center of the Earth. We rarely think of gravity as a cost, yet in the realm of space exploration, it is the ultimate tax, a physical levy that must be paid in raw energy before the universe allows you to go anywhere else. This is established science. This is not speculation. To understand why the first people on Mars may never return, we must first understand the physics of what scientists call the gravity well. Imagine for a moment that the solar system is not a flat map, but a vast invisible landscape of pits and valleys. Every planet, moon and star sits at the bottom of its own pit. The more massive the object, the deeper and steeper the pit it creates in the fabric of space-time. Earth sits at the bottom of a very deep, very steep valley. The Moon sits in a shallow, gentle dip. Mars sits in a pit that is shallower than Earth's, but significantly deeper and more dangerous than the Moon's. This is confirmed physics. Leaving a planet is essentially a climb out of this pit. The energy you need to reach the top and break free is what we call escape velocity. For Earth, that speed is 11.2 kilometers per second. 11.2 kilometers per second. In the time it takes you to blink, a rocket leaving Earth must travel nearly 7 miles. That is roughly 25,000 miles per hour. To give that number a domestic scale, you can visualize. Think of a bullet fired from a high-powered rifle. It travels at about 1,800 miles per hour. Escape velocity from Earth is more than 13 times faster than a bullet. This is the tax Earth demands. It is why our rockets are so enormous. Over 90% of a Saturn V's weight was nothing but the chemical energy needed to climb out of Earth's pit. Our collective mental model for returning from another world is based entirely on the Apollo missions. We remember the 12 astronauts who walked on the Moon and returned home safely. Because we did it in 1969, we tend to assume Mars is just a similar challenge. Perhaps a bit harder, but fundamentally the same category of problem. The data shows this assumption is deeply wrong. The Moon and Mars are fundamentally different categories of difficulty because of how hard each world holds on to you. The Moon's escape velocity is about 2.4 kilometers per second. This is fast, but it is only 1/5 of Earth's. Because the Moon is small, about 1/80,000th of Earth's mass, its gravity is weak and it has no atmosphere. When the Apollo astronauts wanted to leave, they climbed into a tiny ascent stage that was so flimsy you could poke a finger through the walls if you pushed hard enough. It didn't matter. In that shallow gravity dip, they only needed a modest amount of fuel and an engine burn of just 7 minutes to break free. Mars is a different hard. The measured escape velocity for Mars is 5.03 kilometers per second. 5.03 kilometers per second. That is more than double the speed required to leave the Moon. You might think that a mission requiring twice the speed would simply require twice the effort. But physics does not work linearly. This is the deeper complication. Kinetic energy scales with the square of velocity. This means that when you double the speed you need, you don't double the energy requirement. You quadruple it. Escaping Mars requires approximately 4 to 5 times as much energy per kilogram as escaping the Moon. That is the energy tax. It is a fundamental law of the universe that cannot be negotiated. To visualize what this feels like for mission planners, we use the deep valley and heavy backpack analogy. Imagine you're standing at the bottom of a steep valley. You need to climb to the top to survive. If the valley is shallow, like the Moon, you can carry a light bag and make the climb easily. But Mars is a deep valley with high, crumbling walls. To make it out, you need a massive amount of energy. To get that energy, you need to carry food and water for the climb. But here is the brutal logic of the gravity well. Every litre of water you add to your backpack makes you heavier. Because you are heavier, you now need even more energy to lift yourself and the water. To get that extra energy, you have to pack even more food. But the extra food has its own weight, which makes the climb even harder, requiring still more supplies. This is the cascading weight problem. Every kilogram of crew, every kilogram of life support, and every kilogram of scientific samples you want to bring back from Mars has to be accelerated to that 5.03 kilometers per second. And the fuel you need to achieve that speed also has mass, which requires even more fuel to lift the fuel itself. On the Moon, this snowball effect was small enough to manage with 1960s technology. On Mars, the snowball becomes an avalanche. The data confirms that this is why we have never seen a return trip from Mars. Since the early 1970s, humanity has sent dozens of orbiters, landers, and rovers to the Red Planet. We have seen the Soviet Mars 3, NASA's Viking landers, the Spirit and Opportunity rovers, and the Perseverance rover currently exploring Jezero crater. Every single one of these missions has been a one-way trip. Not a single robot, not a single sample container, not even a test vehicle has ever launched from the surface of Mars and returned to Earth. This is not because we forgot to try or lack the ambition. Engineers have been drafting return plans since 1952. The reason is that the energy tax for leaving Mars is so high that even returning a few tubes of rock, the Mars Sample Return mission, is currently estimated to cost upwards of $7 billion and has been redesigned multiple times because the complexity keeps ballooning. If returning a few hundred grams of soil is a multi-billion-dollar struggle that takes decades of planning, imagine the energy required to return a human crew with all the air, water and food they need to survive for a 9-month journey back. Mars sits in a very specific, very frustrating, bitter spot in our solar system. It is close enough that we can reach it with our current rocket technology, and its gravity is low enough that we can land there. But its gravity is just high enough that leaving is genuinely difficult. There is another invisible factor that makes this launch even harder than a climb out of a pit. Mars has an atmosphere. It is a thin, ghostly atmosphere, less than 1% of the density of Earth's. But it is thick enough to create drag as a rocket tries to ascend. It acts like a headwind that never stops. On some worlds with thick atmospheres, you could theoretically use wings to create lift and help you leave. But on Mars, the atmosphere is too thin to help you, but just thick enough to punish you. It only takes. It never gives. This is why, for the first people on Mars, the return journey is not a simple matter of lighting a fuse and heading home. It is an uphill battle against a quadrupled energy requirement, a cascading fuel problem, and a planet that does not want to let go. This one number, 5.03 kilometers per second, is the foundational constraint of the entire mission. Everything else flows from it. The size of the ship, the cost of the mission and the risk to the crew. Every mission architecture, every NASA study and every private proposal for Mars exploration eventually traces back to this unforgiving energy debt. But even if we could pay the tax, even if we could find a way to carry enough energy to climb out of that deep Martian valley, there is a mathematical barrier that stands in our way. A relationship so punishing that rocket scientists have given it a terrifying name, the tyranny of the rocket equation. This is established mathematics, first derived in 1897, and it dictates that every kilogram you want to bring home doesn't just cost energy, it costs an exponential amount of weight that may eventually make the return journey physically impossible. If we could somehow pay the energy tax and find a way to climb out of that deep Martian valley, we would still find ourselves standing before a mathematical barrier so absolute and so punishing that rocket scientists have given it a name: the tyranny of the rocket equation. This is not a metaphor or a piece of poetic flair. It is a fundamental law of physics derived in a quiet provincial Russian town by a self-educated schoolteacher named Konstantin Tsiolkovsky. The year was 1897. Tsiolkovsky spent his spare time thinking about the mathematics of space travel, decades before anyone had ever built a rocket capable of reaching the upper atmosphere. What he derived was an equation that describes the fundamental relationship between three things: the speed a rocket can achieve, the efficiency of its engines, and the ratio of the fully fueled rocket to the empty ship that remains after the fuel is gone. The formula is elegant in its simplicity, yet it acts as a merciless wall that has dictated the limits of human exploration since the very beginning of the space age. This is established mathematics. This is what the data says. To understand why this equation is described as a tyranny, you have to understand the specific, cruel logic of moving mass through a vacuum. On Earth, if you want your car to go twice as far, you simply double the amount of gas in your tank. The car is slightly heavier, but the difference is negligible. In rocketry, the math does not work linearly, it works exponentially. To move a spacecraft, you need fuel, but fuel itself has mass. To carry that mass, you need more fuel, and to carry the fuel that carries the fuel, you need even more fuel. This creates an exponential snowball effect, where every additional kilogram of cargo you want to bring home doesn't just require 1 more kilogram of fuel, it requires a proportionally larger amount of fuel than the kilogram before it. The requirements do not just grow, they compound. To visualize what this feels like, imagine you are planning a very long hike through a wilderness where there are no sources of food or water. You have to carry everything you need on your back. For a 1-day hike, you pack a single day's worth of food. It is light, and the extra energy you spend carrying it is minimal. But now imagine a hike that lasts for 10 days. You need 10 days of food, which is already heavy. Here is the complication. Because that backpack is now so heavy, you're burning more calories just to haul it over the rough terrain. To get those extra calories, you have to pack even more food. But that extra food has its own weight, which requires even more energy to carry, which means you need to add still more food. For a very long journey, you eventually reach a point of absurdity where the vast majority of your backpack is filled with food that exists solely to provide the energy needed to carry the food. The actual supplies you need for yourself, the reason you're taking the hike, become a tiny, almost insignificant fraction of the total load. This is exactly what happens with rockets. The math is unforgiving. Consider the most powerful machine humanity has ever successfully flown to completion, the Saturn V. This was the rocket that sent 12 human beings to the surface of the moon. When that rocket stood on the launch pad at Cape Kennedy, it was a towering monument to engineering, standing 363 feet tall. It weighed 6.5 million pounds fully fueled. Let that number settle for a moment. 6.5 million pounds. In the time it takes you to hear this sentence, the first stage of that rocket was designed to burn through 5 million pounds of fuel in just under 3 minutes. But here is the measurement that truly reveals the tyranny. Roughly 85 to 93% of that massive 6.5 million pound structure was nothing but fuel and oxidizer. The actual spacecraft that finally returned to Earth, the tiny command module containing the 3 astronauts, weighed only about 13,000 pounds. The rocket was nearly 500 times heavier than the payload that actually came home. That is what gravity and the rocket equation demand for a journey as easy as the moon. Now, we must apply this same merciless mathematics to Mars. Because Mars is a different hard, the gear ratios of the rocket equation begin to spiral into the realm of the physically impossible. To understand the scale of the challenge, we use what engineers call the 226:1 ratio. This is confirmed science. For every 1 kilogram of fuel you want to have waiting on the surface of Mars to fuel your return journey, you must launch approximately 226 kilograms of mass from the surface of Earth. Think about what that means in a domestic scale you can visualize. Imagine you're going on a road trip and you need to bring a 5-gallon can of gas for the return leg. To get that 5 gallons of gas to your destination, the laws of physics on Mars demand that you start your trip with 1,130 gallons of gas just to carry the extra weight of that 5-gallon can. If your return spacecraft is quite lean, let's say it has a dry mass of 10,000 kilograms, which is very small for a ship that must keep a crew alive for months, the rocket equation tells us you will need roughly 70,000 kilograms of propellant sitting on the surface of Mars, loaded and ready to go. To get those 70 tons of fuel from Earth to the Martian surface, accounting for the energy needed to leave Earth, travel through deep space, and land safely, you would need to launch something like 1.4 million kilograms of total mass from Earth's surface. This would require multiple launches of the largest rockets ever built, just to deliver the gas for the trip home. This is the cascading nature of the problem. Each stage of the journey multiplies the demands of the stages that follow. The costs do not just add up, they multiply. NASA and private companies have run these calculations repeatedly. When they look at the mass requirements for a crewed mission with a guaranteed return capability, They arrive at mission masses in low Earth orbit that are 5 to 10 times larger than the entire Apollo program. Estimates for the cost of a single round-trip mission range from $100 billion to $500 billion. This is why, since the early 1970s, every single mission we have ever sent to Mars has been a one-way trip. From the Viking landers to the Perseverance rover, every machine we have placed on that red soil is still there and will be there forever. We have never brought back a single gram of Martian soil, not because we lack the will, but because the mathematical tax of the rocket equation is a debt we have not yet found a way to pay. This relationship is as inviolable as gravity itself. It sets hard limits on what chemical rockets can do. You cannot negotiate with it. You cannot engineer your way around it. You can only work within its limits or find a fundamentally different approach. For the first people on Mars, the weight of this math is the second reason they may never return. Even if they survive the silence of the signal, they are trapped by the sheer mass of the fuel required to leave. This has led many mission architects to suggest a radical, elegant solution. Instead of bringing the fuel from Earth, we will simply build a factory and manufacture it on Mars. This is known as ISRU, or In Situ Resource Utilization. It sounds like the perfect escape from the tyranny of the rocket equation. We land, we build, we fuel up, and we come home. But this solution introduces a new, even more terrifying complication, a logistical threshold that engineers call the maintenance paradox. Because for a human crew to have a ride home, that chemical factory has to land on Mars and operate perfectly, all by itself for 2 years before a single human hand is ever there to fix it. If we are ever to overcome the mathematical wall of the rocket equation, we must embrace a solution that sounds, at first, like an elegant victory over the laws of physics. Since we cannot afford the energy tax required to carry our return fuel from Earth, mission architects have proposed that we simply stop trying to bring it with us. Instead, we will live off the land. This is known as In Situ Resource Utilization, or ISRU. This is not a speculative dream found only in the pages of science fiction. This is established chemistry, first described in 1902 by the Nobel Prize-winning chemist Paul Sabatier. The plan is remarkably elegant in its simplicity. Mars has an atmosphere that is roughly 96% carbon dioxide. We also know, confirmed by orbital measurements and landing data, that the Martian soil contains significant deposits of water ice. By landing a robotic chemical factory on the surface, we can combine that atmospheric carbon dioxide with hydrogen, extracted from the ice to produce two very specific things: methane and liquid oxygen. These happen to be the exact propellants required to power the engines of a return vehicle such as SpaceX's Starship. In theory, Mars itself becomes our fuel depot. We land, we manufacture, we fuel up, and we come home. But this elegant solution introduces a new, even more terrifying complication, a logistical threshold that engineers call the maintenance paradox. To understand this paradox, you have to look at the timeline of a Mars mission, a sequence of events dictated by the narrow launch windows that open only once every 26 months. For a human crew to arrive on Mars with a guaranteed ride home, the fuel processing factory cannot arrive with them. It has to land first. In fact, it must land, deploy its solar panels or nuclear reactors, extract its water, and complete its chemical production of tens of thousands of kilograms of fuel before the crew even launches from Earth. This is what mission planners call the 24-month waiting problem. Right now, as you sit in the safety of your home, try to visualize that factory. It is a complex industrial-scale chemical plant sitting entirely alone on a dead world 140 million miles away. There is no space police or maintenance crew to check on it. There are no technicians to tighten a loose bolt, no engineers to clear a clogged sensor, and no one to swap out a degraded seal. This is confirmed science. For 2 full Earth years, this machine must operate perfectly, all by itself, in an environment that is actively designed to destroy precision engineering. The Martian environment is not a static desert. It is a landscape of brutal, relentless thermal cycling. Near the equator, during a summer day, the temperature might reach a relatively mild 20 degrees Celsius, but the moment the sun dips below the horizon, the thin atmosphere, less than 1% the density of Earth's, fails to hold any heat. The temperature plummets to minus 100 degrees Celsius or lower. This is not speculation. These measurements have been recorded by every lander we have ever sent. Every single day for 730 days, every component of that fuel factory must expand and contract as it swings through a temperature range of 120 degrees. Think about the metal in the valves. Think about the gaskets and the seals. On Earth, we struggle to build machines that can run unattended for 2 years in a climate-controlled warehouse. On Mars, we're asking a machine to do industrial chemistry while being frozen and thawed over 700 times. And while the temperature is attacking the structure, the dust is attacking the mechanics. Martian dust is not like the dust in your house. It is extraordinarily fine, with particles as small as a few micrometers, roughly the size of the particles in cigarette smoke. Because Mars has no humidity to ground these particles, they carry a persistent electrostatic charge. This means the dust does not just settle, it clings. It is attracted to solar panels, reducing their power output. It infiltrates the smallest gaps in mechanical joints. Most importantly, this dust contains perchlorates. These are toxic, highly reactive chlorine-based compounds that are confirmed to be spread across the entire planet. Perchlorates are corrosive. As the fuel factory sits alone, these reactive chemicals are accumulating on its valves and eating away at the very seals that must hold back the high-pressure gases of the Sabatier reaction. The data from the Mars exploration rover Opportunity provides a sobering case study. Opportunity was a masterpiece of engineering, surviving for 14 years on the Martian surface. But in 2018, a global dust storm shrouded the planet for months, blocking the sun and draining the rover's batteries until its heaters could no longer fight the cold. The machine froze and never woke up. A fuel production plant faces this same fundamental vulnerability. A single dust storm at the wrong moment could shut down production, or worse, cause a critical component to fail while the crew is still millions of miles away. This leads us to the heart of the paradox, the mean time between failure, MTBE. Every mechanical system has a design life, a statistical window in which it is expected to work before something inevitably breaks. By the time the human crew finally arrives on Mars, their ride home, the Mars Ascent vehicle has already lived its entire design life entirely alone. The crew will land and look at a rocket that has been sitting in the perchlorate dust, endured 700 cycles of deep freeze temperatures, and operated its internal plumbing for 2 years without a single maintenance check. The mystery that every mission planner must face is this: can a machine that has already reached its statistical failure threshold still fire on the first try? In rocketry, there are no warm-ups. There is no test firing of the return engine because we cannot afford to waste a single kilogram of the fuel we spent 2 years manufacturing. The first time those engines ignite will be the moment the crew's lives depend on it. On Earth, a rocket launch is supported by an army of thousands of engineers, technicians, and safety officers who check every valve and sensor until the final second of the countdown. On Mars, there is only the silence of the desert and a machine that has been waiting in the dark for years. If a fuel line is clogged by electrostatic dust, if a valve has been corroded by perchlorates, or if a sensor gives a false reading due to radiation damage, the result is not a delay, it is a death sentence. The crew is either off the surface in 7 minutes, or they are stranded for another 26 months, hoping their dwindling life support can outlast the Martian winter. This is why the maintenance paradox is one of the most profound reasons why the first people on Mars may never return. It is the reality that our very best systems for saving the crew are most likely to fail at the exact moment the crew arrives to depend on them. But even if the machinery holds, even if the factory produces the fuel and the engines ignite perfectly, there is another tax being collected that we cannot see. a tax that is not paid in kilograms of methane, but in the micro-architecture of the human body itself. Because while the machines are sitting on the surface accumulating dust, the humans in transit are experiencing a biological remodeling that might make the very idea of a return a physical impossibility. This is confirmed science, and it begins with the very thing that holds you upright in your chair right now, your skeleton. Right now, as you listen to this, you're participating in a quiet biological negotiation. You feel the weight of your arms resting at your side, the pressure of your back against your chair, and the firm contact of your feet upon the floor. This is the constant pull of Earth's gravity, a force your body has known since the moment of your conception. It is so familiar that you do not even perceive it as an influence, yet every cell in your body is currently reacting to it. Your muscles are firing in micro-adjustments to keep you upright, and your heart is working at a specific pressure to push blood against this downward pull and into your brain. But the most profound reaction is happening deep inside you, within the very architecture of your bones. This is established science. Our bodies are not static machines. They are living ecosystems designed to optimize themselves for the environment they inhabit. When the first people on Mars step out onto that red soil, they will experience a physical sensation that many have dreamed of for decades. The lightness of a world with 38% gravity. 38%. In the time it takes you to absorb that number, visualize what it means for a human frame. If you weigh 180 pounds on Earth, you will weigh just 68 pounds on the surface of Mars. You could jump higher, lift heavy equipment with ease, and move with a buoyancy that feels like a permanent release from a lifelong burden. On the surface, it sounds manageable, perhaps even pleasant, but the data shows that this lightness is a mask for a process of biological dissolution that begins the moment you leave Earth's gravitational well. To understand why the return journey may be a physical impossibility, we must first understand that your skeleton is not a dead mineral scaffolding. It is a living reactive system. This is confirmed science. Inside your bones, two types of cells are engaged in a constant lifelong war. There are osteoclasts, which exist to dissolve and remove old bone tissue, and osteoblasts, which work to build new bone in its place. In the 1G environment of Earth, these two forces are perfectly balanced. Every time you walk, stand, or lift an object, gravity creates mechanical stress on your bones. Your body interprets this stress as a signal that the bone is needed, and the osteoblasts respond by maintaining the density and strength of that scaffolding. On Mars, that signal is silenced. When the mechanical load of gravity is reduced by 62%, your body makes a logical, yet devastating biological decision. It determines that maintaining a heavy, dense skeleton is no longer metabolically efficient. Maintaining bone is expensive for the body in terms of energy and nutrients. In the thin gravity of Mars, your body decides it simply does not need that much support. The osteoclasts continue their work, dissolving the bone on schedule, but the osteoblasts, the builders, fall silent. The living scaffolding begins to melt away. The scale of this decay has been measured directly on the International Space Station. This is not speculation. Astronauts in microgravity lose bone mineral density at a rate of 1 to 2%. 1 to 2% every single month. To humanize that number, think of a standard 6-month stay on the ISS. An astronaut returns to Earth having lost roughly 10% of their bone mass in the weight-bearing regions of their skeleton, the hips, the legs, and the lower spine. This is comparable to the bone loss an elderly person with advanced osteoporosis might experience over an entire decade, and that is after only half a year. Now, apply this measurement to the timeline of a Mars mission. The journey there takes roughly 9 months in total weightlessness. By the time the crew's boots first touch Martian dust, they have already lost up to 15% of their skeletal density. They then spend 500 days, over 16 months, on the surface in 38% gravity. While Mars gravity is better than the nothingness of the transit, it is confirmed by NASA research that 38% is likely below the threshold, required to maintain human musculoskeletal health. The bones continue to thin. Then they must endure another 9 months of microgravity for the return journey. By the time that crew finally sees the blue horizon of Earth through their portholes, they will have spent nearly 3 years away from the gravity that built them. The cumulative loss could be as high as 20 to 30%. This is where we must face the analogy of the skeleton of a stranger. Imagine an astronaut who launches for Mars in their early 30s. They're in the peak of their physical life. But after 3 years in the Martian environment, their body has conducted a radical remodeling of its internal structure. They might return to Earth with the brittle, porous microarchitecture of an 80-year-old. If you could zoom in and look at the cross-section of their femur, you would see that the internal structure, the honeycomb of mineralized tissue called trabecular bone, has been thinned out. The struts of the bone are no longer thick and interconnected. They are thin, sparse, and fragile. This is what the data says. While some density can be regained through years of rehabilitation on Earth, the microarchitecture of the bone may be permanently altered. They are returning to Earth in a body that they no longer recognize. The return to Earth, then, is not a homecoming. It is a violent physical collision. Earth gravity, which you feel right now as a gentle, unnoticed presence, would become a crushing, lethal force to a Mars-adapted skeleton. Re-entry into Earth's atmosphere is a high-G event. The spacecraft decelerates from 25,000 miles per hour to 0 in a matter of minutes. During this time, the crew is subjected to forces several times the weight of normal gravity. For a healthy person, it is a brutal but survivable strain. For a crew member whose bones have become as fragile as glass, those G-forces could cause spontaneous fractures. Their spine, which has expanded and softened over 3 years, may no longer be able to protect their spinal cord under the sudden, massive compressive load of re-entry. Even if they survive the landing, the physical betrayal continues. On Earth, after 6 months on the ISS, many astronauts cannot stand or walk without assistance. They experience orthostatic intolerance, a condition where the heart, which has also atrophied and become smaller in the low-gravity environment, cannot pump blood effectively against Earth's full 1G pull. The blood pools in their legs, their brain is starved of oxygen, they faint. Now, multiply that deconditioning by 6. The heart of a returning Mars explorer has become optimized for a world that does not exist on Earth. It has become a Martian heart. The moment they step back onto the homeworld, that heart may simply be too small, too weak, and too deconditioned to keep them conscious. Their muscles, which have atrophied by up to 20% despite 2 hours of daily exercise in space, will strain to move a body that now feels 3 times heavier than it did for the last 500 days. This is the physiological point of no return. It is the realization that your own biology may close the door behind you. You adapt so perfectly to Mars that you effectively exile yourself from Earth. This is confirmed science, and it represents a biological one-way trip that exists independently of the engines or the fuel. But there is an even more unsettling layer to this biological remodeling. It is something that happens not to the bones or the heart, but to the very seat of your identity, your brain. While the gravity is thinning your bones, another invisible force is silently rewriting the neural pathways that make you who you are. This is the reality of galactic cosmic rays, high-energy particles from distant supernovae that pass through the hull of a ship as if it were made of paper. And as you will discover in the next chapter, they are already at work, physically altering the minds of the people who will one day call Mars home. Right now, as you lie in the quiet safety of your room, you are being protected by a shield you cannot see. Above you, stretching tens of thousands of kilometers into the dark, Earth's magnetic field is busy deflecting a relentless rain of high-energy particles. Beneath that, 100 kilometers of atmosphere acts as a thick protective blanket, absorbing the radiation that manages to slip through. Together, these two shields reduce the radiation dose you receive right now to a level so low that your body's repair mechanisms can fix the damage almost as fast as it occurs. This is established science. and it is the only reason human biology has been allowed to flourish on this world. But the moment you leave this protective cocoon, the rules of survival change. To cross the 140 million mile gap to Mars is to step into a shooting gallery where the bullets are invisible, travel at nearly the speed of light, and pass through solid metal as if it were tissue paper. This is confirmed by data from every mission that has ever left low Earth orbit. The most profound threat to the first people on Mars isn't just to their bones or their hearts. It is a threat to the very seat of their identity, their brain. The investigation into this hidden cost begins with a phenomenon known as galactic cosmic rays, or GCRs. These are not particles from our Sun. They are the remnants of ancient, violent cosmic events, supernovae that occurred millions of years ago in distant parts of the galaxy. They are the nuclei of atoms stripped of their electrons and accelerated to relativistic speeds by the unimaginable power of dying stars. Because they are travelling so fast, they carry an enormous amount of kinetic energy. When one of these particles hits a human cell, it doesn't just damage it. It smashes through it like a bowling ball through a set of pins, shattering DNA strands and creating cascades of secondary damage. This is the established reality of deep space. On Earth, you might receive a radiation dose of roughly 3 millisieverts over an entire year. In the void between planets, you receive that same dose every day and a half. To visualize the scale of this, imagine you're sitting in a room where every second thousands of microscopic high-speed needles are passing through your body. You feel nothing. There is no heat, no pain, and no sound. But at the subatomic level, your biological architecture is being systematically dismantled. This is not speculation. It is measured data from NASA's Radiation Assessment Detector, which recorded these levels during its journey to the Red Planet. As we plan these missions, we naturally look to shielding as the solution. We imagine that by building thicker hulls or using specialized materials, we can protect the crew. However, this leads us to a complication that is as counterintuitive as it is terrifying. In the specific physics of space radiation, the very shield you build to save you can actually make the danger worse. Most spacecraft are currently built with aluminum hulls because the material is light and strong. But when a high-energy galactic cosmic ray strikes an aluminum atom, it doesn't always stop. Instead, it shatters the aluminum nucleus, triggering a process called secondary spallation. This creates a shower of secondary particles, neutrons, protons, and pions, that scatter inside the cabin. These secondary particles are often more biologically damaging than the original cosmic ray would have been on its own. This is confirmed science. If your shielding is too thin, it acts as a multiplier for the radiation, turning a single incoming particle into a spray of shrapnel that riddles the crew's bodies. To meaningfully reduce this exposure, you would need several meters of shielding, perhaps a hull made of 5 feet of solid water or thick lead. But the weight of such a ship would be so great that the rocket equation would make it impossible to launch. So the first people on Mars will travel in ships that offer only marginal protection. They will live inside this invisible rain for 9 months on the way there, for 500 days on the surface, and for another 9 months on the way back. This leads us to the deeper layer of the investigation, what this does to the human mind. For years we worried about cancer. We calculated the risk that an astronaut would develop a tumour a decade after returning home, but recent research has shifted the focus to a more immediate space brain crisis. This is based on confirmed studies from the University of California, Irvine, where researchers used particle accelerators to mimic the Martian radiation environment. They exposed mice to the same types of heavy ions found in galactic cosmic rays, and then observed their behaviour. The results were startling. The irradiated animals showed persistent cognitive decline and memory erosion. They displayed increased anxiety and a reduced ability to learn new tasks. Perhaps most disturbingly, they exhibited behaviours that, in humans, are consistent with the early stages of dementia. When the researchers looked at the brains of these mice under a microscope, they saw the physical reason for this decline. The The radiation had physically pruned the dendritic spines, the tiny branching structures on neurons that allow them to communicate with each other. It was as if the wiring of the brain was being systematically cut. In some regions, like the hippocampus, which is responsible for memory and spatial navigation, the density of these connections had dropped significantly. This is the established data. And while humans are not mice, our neurons function in the same fundamental way. The researchers concluded that for a human crew travelling to Mars, there is a high statistical probability that at least one member will return with severe cognitive deficits. Think about the implications of this for a moment. You're 140 million miles from Earth. You're living in a habitat where a single wrong button press or a forgotten maintenance protocol could kill the entire crew. You're in a high-stakes, high-stress environment that demands peak mental performance every second of every day. And yet, while you sleep, invisible particles are passing through your skull and physically rewriting your neural pathways. Your memory is eroding. Your ability to solve complex problems is slowing down. Your personality may even be shifting as the prefrontal cortex, the part of the brain that regulates social behavior and impulses, is degraded by the particle rain. This is the invisible fact of the mission. Radiation is not just a long-term cancer risk. It is an active, ongoing assault on the very hardware of your consciousness. And here is the most unsettling part. You wouldn't feel it happening. Cognitive degradation is not like a broken leg. You don't look down and see the damage. You simply become slightly less sharp, slightly more forgetful, and slightly less yourself. You have no way of knowing how much of your original self has been stripped away by the distance you've travelled. This creates a psychological feedback loop. The crew will know they are under assault. They will know that every month they spend on Mars, their brains are becoming less capable of making the decisions required to get them home. This realization can trigger chronic stress and paranoia, which only accelerates the decline. Is there a resolution? Not a full one. We are researching pharmaceutical countermeasures, antioxidants and drugs designed to protect DNA, but as of now, nothing has proven effective against the relentless energy of galactic cosmic rays. We are looking at storm shelters, where the crew can hide during solar flares, but these offer no protection against the constant background GCRs that pass through almost everything. This is established physics. The universe has set a specific price for crossing the gap between worlds, and part of that price is paid in the architecture of the human mind. We are essentially sending our best and brightest into a meat grinder for the human soul. We are betting their lives and their identities on the hope that the damage won't be too much before they can complete the mission. But even if the mind adapts to the radiation, and the body survives the thinning of the bones, there is another wall that stands in the way. A wall that isn't made of particles or gravity, but of something even more absolute: time. Because even if you are still you when you reach the red planet, the version of Earth you left behind is already beginning to disappear. This is the information shadow, and it is the reason why even the most successful Mars mission will eventually feel like an exile. Right now, as you listen to this, you are part of a global, instantaneous web of thought. If you send a text to someone on the other side of the planet, they receive it before you have even finished your next breath. If a major event occurs in a city thousands of miles away, you can watch it unfold in high definition, in real time. This shared present is the invisible fabric of modern human civilization. It is so fundamental to our experience of reality that we rarely notice it. Yet it is the very thing that the first people on Mars will lose the moment they cross the 140 million mile gap. This investigation into the psychological exile of the red planet begins with a physical barrier that no technology can overcome. The wall of light minutes. This is established physics. This is not speculation. The speed of light, roughly 186,000 miles per second, is the absolute cosmic speed limit. On Earth, we are small enough that this limit feels like an instant. But as you move into the solar system, the scale of the universe begins to swallow the speed of light. The Moon is roughly 239,000 miles away, a distance light can cover in about 1.3 seconds. This is why the Apollo astronauts could have conversations with Houston. There was a slight pause, a heartbeat of delay, but the rhythm of human exchange remained intact. Mars offers no such mercy. The measured data shows that at its closest approach, Mars is 34 million miles away, creating a one-way signal delay of roughly 3 minutes. At its farthest point, when the two planets sit on opposite sides of the Sun, that delay swells to 22 minutes. This means a simple exchange, a question followed by an answer, takes at least 44 minutes. To visualize what this feels like, think about a standard phone call with a half-second satellite lag. You talk over each other, you lose the flow, you feel a growing frustration as the social feedback loop breaks. Now multiply that frustration by over 2,600. On Mars, communication is not a conversation, it is correspondence. It is closer to writing a letter and waiting for the mail to arrive than it is to any form of human interaction our species has evolved to understand. This temporal wall is not just a social inconvenience, it changes the fundamental nature of survival. To understand why, we must look at a specific historical moment, April 13th, 1970. When an oxygen tank exploded aboard Apollo 13, the crew reported the problem instantly. "Okay, Houston, we've had a problem here." Because the moon is close, Mission Control heard those words less than 2 seconds after they were spoken. Telemetry data streamed into Houston in real time, allowing hundreds of the world's best engineers to see exactly what the astronauts were seeing as it happened. This real-time loop provided a cognitive surplus, a second brain on Earth that could calculate trajectories and troubleshoot systems, while the crew managed their own fear and exhaustion. That link saved 3 lives. Now, replay that exact scenario on the surface of Mars. An explosion occurs, a pressure seal in the habitat fails, and the atmospheric alarm triggers. The commander keys the microphone and reports the emergency. That signal leaves the spacecraft and begins its long journey through the void. For the next 14 minutes, the crew is entirely terrifyingly alone with the crisis. They must diagnose the failure, assess their oxygen reserves, and begin a fix before their distress call even reaches the ears of an engineer on Earth. By the time Houston receives the message and formulates a response, 28 minutes have passed since the alarm first sounded. In a situation where seconds matter, the crew is either already alive because they solved it themselves, or they are dead because they could not. This is confirmed by NASA's own research. Earth is removed from the decision-making chain during a Mars mission. Earth can only listen to the sound of a past that has already ended. On Mars, Mission Control is not a safety net, it is a historian. But there is a deeper layer to this investigation, a period of isolation so total that it represents a complete informational exile. It is known as solar conjunction. Approximately every 26 months, the orbits of Earth and Mars align so that the Sun sits directly between the two planets. This is not speculation. It is an unnegotiable fact of orbital mechanics. For a period of roughly 2 to 3 weeks, the Sun's intense radiation, the corona, disrupts and blocks all radio waves passing through it. During these weeks, the crew on Mars is not just delayed, they are blacked out. No data transmissions, no telemetry, no emergency signals, no voices from home. Think about the psychological weight of those 2 weeks. On Earth, we regulate our emotional states through connection. We check the news, we call a friend, we look for confirmation that the world is still there. For a Mars crew deep into a surface stay, when the novelty of the red planet has already been replaced by the monotony of survival, the conjunction blackout is a sustained psychological endurance test. Imagine a medical emergency occurs during this period. A crew member develops symptoms of a stroke or acute appendicitis. On the ISS, a flight surgeon would guide the treatment in real time. During conjunction, the crew's medical officer must make a life or death diagnosis and perform treatment with zero input from the thousands of physicians and specialists on Earth. Whatever decision they make alone, and they live or die with the consequences in total silence. This isolation extends into the very texture of your personal identity. On Earth, your relationships are built on shared time. You experience the same seasons, the same news cycles, and the same cultural moments as the people you love. But a Mars crew exists in a parallel timeline. Because of the light-minute delay, you cannot watch a live broadcast. You cannot join a video call with your family. You cannot share a meal over a screen in real time. Every interaction you have with the people you left behind is a recording of a past that has already moved on. This creates what researchers call the emotional trigger of asynchrony. Imagine you receive a video message from your spouse on Earth. In the recording, they look older than you remember. Perhaps there are new lines around their eyes, or their hair has begun to grey. You're watching them age in 14-minute fragments that are already out of sync with your reality. You record a message of love in response, but as you hit send, you realise that by the time they hear those words, they will have lived through nearly half an hour of life that you did not share. As the months turn into years, the bonds that connect you to Earth do not snap, they stretch. They become thin and translucent. People on Earth continue their routines. Seasons change, holidays come and go, and the restaurants you once loved close and are replaced by businesses you will never visit. You become an observer of your own life rather than a participant in it. The data from Antarctic research stations shows that this gradual disconnection is psychologically distinct from the acute stress of an emergency. Emergency stress is intense but focused. Disconnection stress is ambient. It seeps into everything. It is the quiet, corrosive feeling of knowing that the world you belong to is continuing effectively without you, and that you are slowly, imperceptibly becoming someone who belongs to Mars more than to Earth. This is the most profound reason why the first people on Mars may never return. It is not just about the physics of the journey. It is about the quiet redefinition of what it means to be human in a place where home is just a star. By the time the launch window for the return journey finally opens, 500 days into the surface stay, the version of Earth the crew carries in their hearts may no longer exist. They will have crossed an invisible line where leaving becomes its own kind of arrival, and arrival becomes its own kind of loss. Say, to survive on Mars, the crew must invest emotionally in where they are, the habitat, the landscape, and each other, simply to keep going. Every unit of emotional energy directed toward Mars is a unit withdrawn from Earth. You adapt. You normalize the butterscotch sky and the recycled air. You find satisfaction in the work of survival, and in doing so, you effectively exile yourself from the world that built you. This informational shadow is the third layer of the investigation. It is the realization that the distance between worlds is not measured in miles, but in the slow dissolution of human connection. But as we will discover, even if you can survive the silence and the isolation, the very process of choosing who goes on this journey reveals a paradox that may doom the mission before it even launches. Because the type of person stable enough to survive the silence of Mars may be the very person least likely to leave Earth behind forever. Right now, as you sit in the familiar quiet of your room, you are defined by the people who know where you are. If you were to disappear, a network of concern would instantly activate. Your family would call, your friends would look for you, your absence would create a hole in the fabric of your community. This is the weight of being human on Earth. We are anchored to our world by thousands of invisible threads of connection and responsibility. We rarely think of these ties as a constraint, yet in the realm of Mars colonization, they represent the most difficult variable to solve. To understand why the first people on Mars may never return, we must investigate the specific and often contradictory psychology required to even consider the journey. This investigation begins with a confirmed number that shocked mission planners when it was first recorded. In 2013, a project called Mars One issued an open call for volunteers willing to make a one-way trip to the Red Planet. They were explicit. There was no return mission. If you went, you would live out your remaining years on Mars and eventually be buried in its soil. The organisers expected a few thousand applications from fringe enthusiasts, Instead, they received over 200,000. 200,000. In the time it takes you to hear that number, try to visualize a mid-sized city of people, teachers, doctors, engineers, and students, all willing to leave everything they have ever known behind forever. This is not speculation. The data shows that a significant portion of our species possesses a deep, almost irrational urge to cross the next horizon, regardless of the cost. When researchers studied the profiles of these volunteers, they identified a consistent psychological signature. These individuals scored remarkably high in a trait known as openness to experience. They possessed an elevated tolerance for ambiguity and a high degree of self-transcendence, the ability to find meaning in a purpose that extends beyond their own individual survival. They were not running from Earth. They were running toward a chance to be the beginning of something that might last forever. But this discovery phase of recruitment masks a deeper complication that has been measured in the most isolated places on our own planet. To understand it, we must look at the data from the researchers who spend their winters at the Amundsen Scott South Pole Station in Antarctica. In long-duration isolation, there is a phenomenon known as the third quarter phenomenon. This is established science. Whether a mission lasts 6 months or 3 years, morale does not decline linearly. Instead, there is a sharp, measurable crash that occurs roughly 75% of the way through the assignment. To visualize what this feels like, imagine you're on a very long, difficult hike. At the beginning, the novelty and the adrenaline of the challenge carry you forward. Near the end, the proximity of the finish line provides a final burst of energy. But the third quarter is the dead zone. The novelty of Mars, the butterscotch sky and the pink sunsets, has worn off and become the background monotony of your survival. The end of the mission is not yet close enough to feel real. This is confirmed data. In this window, irritability spikes. Sleep patterns deteriorate. Interpersonal tensions that were manageable in the first few months become explosive. In the confined space of a Mars habitat, you cannot take a walk to clear your head. You're trapped with the same 4 or 6 faces, hearing the same stories for the 1,000th time, knowing that your survival depends entirely on people you may have grown to resent. On Earth, the third quarter phenomenon eventually passes because the mission ends. The researchers fly home, but on a permanent relocation to Mars, the third quarter never ends. There is no finish line. There is only the accumulation of the ambient stress of knowing you are 140 million miles away from a safety net that no longer exists. This leads us to the deepest layer of the investigation, the selection paradox. To build a successful Mars colony, mission planners need a very specific kind of human being. They need someone who is psychologically stable, someone with high emotional regulation, a strong sense of conscientiousness, and the ability to work in a team under extreme pressure for years. This is established criteria. Here is the paradox. The most stable, well-adjusted people on Earth are usually the ones with the deepest ties to it. They have healthy families, they have successful careers, they have robust social networks and a sense of belonging to their community. Because they are so well-adjusted, they are the very people who have the most to lose by leaving, and therefore, they are the people most likely to want a return ticket. Their stability is anchored in the very world they would be asked to abandon. On the other hand, the individuals most willing to volunteer for a one-way trip, those who are ready to say goodbye to Earth forever without a second thought, are often the people with the fewest ties to our world. They may be people who have struggled to build lasting connections, or people seeking to escape a reality they find unfulfilling. This creates a terrifying statistical reality for mission planners. If you select for willingness to exile, you may inadvertently be selecting for the very traits that make someone least suited for the crushing, isolated confinement of a Mars habitat. The data from submarine crews and Antarctic stations shows that loners, or people who lack strong social anchors, do not actually thrive in isolation. They tend to withdraw further, becoming what researchers call autonomized, disconnected from the group and less likely to follow the life-critical protocols that keep everyone alive. The ideal Mars colonist is someone who's detached enough from Earth to leave it, but attached enough to their crew to survive with them. This is a vanishingly narrow psychological profile. It is possible that the number of humans who actually fit this description is so small that we cannot populate a sustainable colony with them. Think about the implications of this for a moment. We are planning a mission that requires the most brilliant, most stable members of our species to act like functional sociopaths. We are asking them to look at the pale blue dot of Earth and feel nothing but the abstract satisfaction of a job well done. We are asking them to watch their parents grow old and die in 20-minute delayed video fragments and still show up for their shift to check the oxygen scrubbers. This is the established data. You cannot train away the basic human need for connection. You can only suppress it. And when that suppression fails, as it almost inevitably will during the third quarter of a lifetime on Mars, the result is a psychological breakdown on a world that offers no hospital, no sanctuary, and no way home. As the weeks turn into years, the first people on Mars will discover that the hardest thing to leave behind was not the air or the gravity. It was the version of themselves that was capable of belonging to a world that shared their present moment. They will adapt. They will normalize the recycled air and the metallic taste of the water, but in doing so, they will become something other than earthly humans. This biological and psychological remodeling is the fourth layer of the investigation. It is the realization that return is not just a question of fuel or physics. It is the reality that your own heart and spine will eventually remodel themselves so completely for the red planet that Earth's gravity would become a lethal, crushing force. You don't just go to Mars, you become Martian. And as we will discover in the next chapter, that transformation is a threshold from which there is no biological return. Right now, your body is engaged in a continuous, high-stakes conversation with the world around you. Every time you stand up, your heart adjusts its rhythm to keep blood flowing to your brain against the downward pull of gravity. Every time you walk, your bones interpret the impact of your steps as a command to remain dense and strong. This is established science. You're not a finished product, but a biological ecosystem that is constantly being edited by your environment. To understand why the first people on Mars may never return, we must look past the fuel tanks and the rocket engines and investigate a threshold that is far more absolute, the biological point of no return. This is the moment when your body listens so closely to the red planet that it effectively deletes the version of you that was capable of surviving on Earth. This is not speculation. It is what the data from decades of spaceflight research tells us. The investigation into this threshold begins with a confirmed measurement. Mars possesses roughly 38% of Earth's surface gravity. 38%. In the time it takes you to process that number, try to visualize what it means for your own physiology. On Mars, you weigh roughly 1/3 of what you do right now. Your muscles, which were built to haul your full weight through a lifetime of Earth-strength gravity, suddenly find their job has become significantly easier. This sounds manageable, perhaps even liberating, but to your body, it is a signal that your current biological architecture is no longer metabolically efficient. This is the discovery of the biological threshold. Every explorer before this moment, even those who spent a year on the International Space Station, lived with the knowledge that they were merely visiting a low-gravity environment. But on Mars, for a stay that must last at least 500 days due to orbital mechanics, your body stops visiting and begins a process of permanent remodeling. This leads us to the first major complication of the return journey: epigenetic adaptation. This is established biology. Your genes provide the blueprint, but your environment determines which parts of that blueprint are actually used. When the constant stress of Earth's gravity is removed, your body initiates a radical house cleaning of its own systems. It begins to systematically dismantle the living scaffolding of your skeleton. The measurement of this decay is confirmed and precise. On the ISS, astronauts lose between 1 and 2% of their bone mineral density every single month. 1 to 2%. To humanize that number, think of the architecture of a house. Imagine that every month you lived in it, someone quietly removed 1 out of every 50 support beams. For the first few months, the structure remains stable, but after 3 years, the minimum duration of a Mars round trip, up to 30% of your skeletal mass has been dissolved and excreted by your own kidneys. This loss is particularly severe in the weight-bearing regions, your hips, your lower spine, and your legs. This is what the data says. While some density can be regained through years of rehabilitation, the microarchitecture of the bone, the intricate honeycomb-like struts that provide strength, may be permanently altered. You would be returning to Earth with the brittle, porous skeleton of an 80-year-old, regardless of whether you left in your 30s. But while your bones are thinning, your heart is undergoing an even more profound transformation. Your heart is a muscle, and like any muscle, it adapts to the workload it is given. On Earth, your heart works relentlessly to push blood uphill to your brain. On Mars, that work is reduced by 62%. Confirmed by NASA research, the heart of a long-duration astronaut physically remodels itself. It becomes smaller, it becomes more spherical, it becomes, in the most literal sense, a Martian heart. This leads to the terrifying reality of the return journey. The return to Earth is not a gentle homecoming. It is a violent physical collision with a world you're no longer built to inhabit. To a Mars-adapted skeleton, Earth's gravity would be a crushing, lethal force. Re-entry into Earth's atmosphere is a high-G event. As the spacecraft decelerates from 25,000 miles per hour, the crew is subjected to forces several times their normal body weight. For a healthy person, this is a survivable strain. But for a crew member whose bones have become as fragile as glass, those forces could cause spontaneous fractures of the hips or the femurs. Their spine, which has expanded and softened over years in low gravity, may no longer be able to protect the spinal cord under the sudden, massive compressive load of landing. Even if you survive the landing, your Martian heart may betray you the moment you attempt to stand. On Earth, your cardiovascular system must fight to keep blood from pooling in your legs. A heart that has spent 3 years optimized for the weak gravity of Mars may simply be too small and too weak to keep your brain oxygenated in Earth's full 1G pull. This is the established condition of orthostatic intolerance, and after a Mars mission, it could be severe enough to cause immediate and persistent fainting. This is the biological point of no return. It is the realization that your own physiology may close the door behind you. You don't just go to Mars, you become Martian, and Earth, the world that built you, becomes a toxic environment that your body can no longer survive. But there is an even deeper layer to this investigation, one that looks past the changing body to the ultimate finality of the journey. Because while we focus on the struggle to return, we must also face the absolute certainty that for some, the journey will end in the first Martian graves. This is confirmed by the statistics of risk. Every mission architecture includes a fatality probability that would be considered unacceptable in any other human endeavour. NASA's own studies estimate that the excess cancer mortality risk from radiation alone could approach 10%. 1 in 10. Think about what it means to die on a world that has been dead for 3 billion years. There are no hospitals on Mars. There is no rescue mission that can reach you in time. If a pressure seal fails, or if a medical emergency occurs during the 2-week blackout of solar conjunction, you're entirely, terrifyingly alone. The first human being to die on Mars will represent a moment of profound civilizational shift. For the first time in the history of our species, human atoms will become part of another world's soil forever. On Earth, our bodies are part of a closed biological loop. We're made of the Earth, and when we die, we return to it. But the first Martian graves represent the first time human matter is permanently exported from the homeworld. Try to visualize a funeral on Mars. It is a quiet, cramped event conducted in a habitat that smells of recycled air and metallic dust. There is no cemetery to visit, no flowers to leave, and no way for your family on Earth to participate in anything other than a recorded message that arrives 20 minutes after the ceremony has ended. The body cannot be buried in the traditional sense, as the Martian permafrost is as hard as concrete, and digging is a luxury of energy the colony cannot afford. More likely, the remains would be placed in a designated area and covered with rocks, marked with a simple monument that will remain undisturbed for millions of years. This is the deepest reality of the permanent relocation mission. It is the understanding that Mars is not just a destination for your life, but a destination for your physical remains. The moment you decide to stay, you are deciding that your atoms will never return to the world that grew them. You're choosing to be scattered on a planet that offers no shade, no rain, and no memory of the life you left behind. This biological and physical finality is the fourth reason why the first people on Mars may never return. It is not just about the difficulty of building a rocket or manufacturing fuel. It is about the quiet, relentless rewriting of what it means to be human in a place where home is no longer a planet, but a star. But as the first Martian graves are marked, and the first Martian-born children look up at the sky, we are forced to confront one final existential reality. From the surface of the red planet, the world we are so desperately trying to return to is no longer a world at all. It is a coordinate. It is an abstraction. It is a smudge of light that you can cover completely with the tip of your smallest finger. And as we will discover in our final chapter, that perspective changes the meaning of return forever. Right now, as we reach the end of this investigation, you are standing at a threshold that is as much philosophical as it is physical. We have spent this time documenting the thinned bones, the eroded neural pathways, the maintenance paradoxes, and the merciless mathematics of the rocket equation. We have looked clearly at the biological and logistical walls that suggest the first people on Mars may never return to the world that built them. But to truly understand why this journey is so often described as a one-way trip, we must resolve one final question. What does it actually mean to return? This is the partial resolution of our investigation. For the first Martians, return may never be a physical journey across the void. Instead, it becomes what researchers call a memory of a bond, a psychological state where home is no longer a destination you can reach, but a collection of echoes you carry with you. This is not speculation. It is a pattern observed in every sustained human separation, from military deployments to the first pioneers who crossed the Atlantic. They discovered that you can bring a person back to a place, but you can never bring them back to a time. The Earth the crew departed no longer exists by the time they are ready to leave the red planet. The people they knew have aged in those 40-minute intervals. The cultural conversations have moved on. The very rhythm of life on the homeworld has evolved without their participation. To return would be to arrive as a stranger in your own house. This is the deepest meaning of Martian exile. The realization that the version of Earth you carry in your heart is a frozen snapshot of a past that has already ended. But as we face this resolution, we must also encounter a layer of honest uncertainty that could turn this entire enterprise into a moral catastrophe. While we're busy engineering the rockets and habitats for human arrival, science is telling us that Mars may not be the dead, silent desert we once imagined. This investigation into Martian life centers on a specific object currently sitting in Jezero Crater, a rock nicknamed Chayava Falls. This is confirmed data, a peer-reviewed discovery published in the journal Nature. Found by the Perseverance rover in July 2024, this arrowhead-shaped stone contains patterns that geologists on Earth recognize with startling clarity. Using the Pixel instrument to map the rock's chemistry, scientists detected organic carbon compounds, sulfur, and iron. But the most provocative features are the leopard spots, white circles with dark, iron-rich rims. On Earth, these spots are produced almost exclusively by one thing: microbes. They are the chemical calling cards of living organisms that consume organic matter and leave behind a fingerprint in the minerals. While this is not yet a confirmed discovery of alien life, it is the most serious candidate for a biosignature ever found on another world. The data shows that no known non-biological process perfectly fits the arrangement of minerals found inside Chayava Falls. This discovery introduces a terrifying complication to our colonization plans. We are racing to land humans on a world that may already be inhabited. This is established biology. Humans are walking ecosystems carrying roughly 38 trillion bacterial cells on and inside our bodies. We shed skin, we exhale microorganisms, and we leak bacteria from every seal in our life support systems. The moment a human being sets foot on Mars, Earth life arrives in force. If Martian life exists, perhaps hidden meters below the surface in what researchers call the radalytic habitable zone, it could be overwhelmed and erased by our biological invasion before we even know it was there. We risk destroying the most important scientific discovery in human history, the proof that we are not alone, simply because we were too impatient to finish the robotic search. This is the moral weight of the first boot print. We may be about to contaminate an entire living world, committing an act of irreversible destruction that no utilitarian calculation can justify. Yet, despite these uncertainties, the forward momentum of exploration is already in motion. This is not a dream of the distant future. The instruments that will decide the fate of these first explorers are being designed and built right now. We're entering a decade of unprecedented technical development. NASA's Artemis program is currently testing the deep space life support systems on the Moon that will be required for the 1,000-day journey to Mars. The Mars Sample Return mission, despite its ballooning costs and shifting architectures, remains the overriding priority for the scientific community as we seek to bring those tubes of rock back to Earth for analysis in our best laboratories. We are engineering our way toward the red planet, chipping away at the gap between the impossible and the merely difficult. We are researching nuclear thermal propulsion that could cut transit times in half, and testing the solid oxide electrolysis of the MOXIE experiment to prove we can breathe Martian air. The investigation is ongoing, and we are the species doing the work. But when you strip away the budgets, the engines and the biosignatures, you are left with one final, human-scale reality. I want you to try to visualize this final existential beat. Imagine you are standing on the surface of Mars. You have survived the landing, the radiation, and the 2-year wait for a window that may never bring you home. You're suited and helmeted, breathing air that tastes faintly of recycled filters. The ground beneath your boots is the color of old blood, and the horizon is closer and sharper than any you ever saw on Earth. It is early morning. The sun is a small pale disk, casting a light that is noticeably colder and dimmer than the one you remember. The sky is a dusty butterscotch, thinning to lavender at the edges of the world. You look up. In the thin, transparent atmosphere of the Martian day, the stars are still visible, and there, low on the horizon, barely distinguishable from the surrounding points of light, you find it, a faint, pale, blue dot. That dot contains 8 billion people. It contains every book ever written, every piece of music ever composed, and every person you have ever known. Your parents, your childhood home, the smell of rain on hot pavement, and the sound of wind through green trees. All of it is compressed into a single pixel of light. You hold up your hand. You extend your smallest finger at arm's length, and you realize that you can cover the entire human world with just the tip of your fingernail. Everything you have ever loved is hidden behind that tiny sliver of yourself. In that moment, you understand what it truly means to be a Martian. You're not an explorer on a temporary assignment. You're a resident of the distance. You're part of the first generation of our species to live beyond the sensory reach of the world that made us. The silence of the 140 million mile gap is no longer an engineering problem to be solved. It is the fundamental condition of your existence. You have paid the energy tax, you have survived the tyranny of the rocket equation, and you have undergone the biological remodeling of your own heart and bone. You have crossed a line where leaving became its own kind of arrival, and arrival became its own kind of loss. You're small, the universe is enormous, and you're the first human being to know exactly what that feels like. The pale blue dot is not above you. For everyone else who has ever lived, it was the ground beneath their feet. For you, It is a coordinate in the dark, a memory of a home that is now and forever out of reach.